why am I here? That's a good question. I got a strange email in my office some couple of years ago from a character who signed himself Eric from Dartmouth. Now, why somebody called Eric from where the British trained their Royal Navy officers, I have no idea. But that's where we train the officers in England, in Dartmouth. But it turned out to be Eric Fossum, and he asked me a significant question: was I the guy involved with MOS, and was I alive? As you can probably tell, I only answered the first question. I'm going to talk a bit about me, which is my favourite subject, and where I've come from, where I go to, and a bit about the MOS days, and also talk about how I see the future, most of which will happen after I have left the future. When I was at school at the age of 11, I knew this was going to fail. Try it that way. At the age of 11, I went down with pneumonia and meningitis. And I only say this because of two things. One, it was forecast that I'd only live for 10 hours. It shows you how good forecasting is. And also, it changed the way my mind worked, and I didn't know that at the time. I found that maths, sciences were all trivially simple and couldn't understand why other people didn't find them the same. That does not apply to history and geography, just those topics. So after that, I went to school, and at the age of 15 and a half, I left school. And unlike today, where everybody is encouraged to go to university, I did what's called an apprenticeship, which enabled me to go to college one day and one evening a week, and at the same time learn about drawing office procedures, mechanical engineering procedures, and so on. Now, running the two things in parallel, we were in a situation where the laboratory that I worked in was clearly got fed up with me being on the apprenticeship, because they shifted me into a laboratory when I was about 17 to run some aspects of creating optical devices, circular diffraction gratings to be precise. And I went from there to work on a sensor system for circular diffraction gratings. The idea of a circular diffraction grating was to define a straight line. The whole idea for the company, which is associated with electrical industries, was to be able to align the bearings of power generators accurately. The sensor I used was a germanium transistor, and I had to create that by scraping the paint off the cover of the transistor so that it became sensitive to light. And in order to get the position, created vibrating mirrors in order to get the thing to move and find its central position. At the same time, I also worked on microscopes and developed a development of the Max Scherer microscope, which enabled you to measure things very accurately and very quickly. And as I said, in parallel with this, I was also at college, and at 18, finished college and then spent a year at university in London, where I gained effectively qualifications in physics and electronics in the same year, because it seemed the easiest thing to do at the time. So I became a physicist and an electronics engineer with a background in optics as well. At the end of, the early part of 1963, the company decided to close the laboratory. I don't think it was my fault, but it was closed. And I was transferred, one of the few actually, out of the 400 people to be transferred within the company. And I was put into a position of transferring semiconductor devices from GEC in America to AEI in England, at a place called Lincoln. Some of you may have heard of Lincoln, some of you may not. I'm not talking about the one on the coast of Oregon. I got bored with that because there was nothing exciting about picking up a technology and shifting it for me. So I looked for another job and moved to Texas Instruments in England, where I was given a job of developing 3.5 indium antimonide sensors for optical devices for high-speed optical sensing, basically using S-band, if that means anything to anybody these days. And then an opportunity came up, which I thought, why not follow an opportunity? It was an opportunity to move to a company called Plessey, their research lab, to take over running a project. You all have seen one of these, a Vidicon, in the beginning, and I was going into Plessey to do something I had no idea what they were going to ask me to do. Presumably I was selected because I knew about silicon, sensing, optics and electronics, because they wanted me to develop an array of sensors, 72 in one direction and 5 parallel lines. In other words, a 72 by 5 array. That's nothing to you, but nobody had done it before, and nobody knew exactly how it was going to work, because the other specification thrown at me just after I walked through the door, basically, was they wanted each line to scan at 5 megahertz. That also is nothing to you. But then, nobody had done that either with MOS. So we were in a curious situation. I didn't know what I was being thrown at to do, what was being thrown at me to do, so I decided that the best way is to do a bit of work on this and find out if we could do anything with it. MOS was in its infancy, and I joined on the 1st of May 1966. So anybody in here who is 49 or younger wasn't born. I was going to ask those older to stand up, but I wouldn't do that. You have to understand that at the time, the technology was very raw in its infancy. There was no idea of what was to come or how to do it. People talked about putting 2 or 3 gates on the circuit. A couple of dozen devices seemed to be the big thing. What I was asked to do was try and create a device with several thousand devices on a chip. So I thought the best thing to do is not do it all in one go, but to do some experimental work. And I discovered that their idea of a clean room was to put on a white coat and go through a door. Positive pressure clean rooms did not exist. Equally, the training of the staff, and when I went in there, I had a team of physicists and engineers and technicians, and somebody mentioned Savas Chamberlain earlier to me, because they knew him, he worked for me. He claims to have invented CMOS. He joined after we did it. Just on the side. So the clean room was non-existent, and in those days it was all hand processing. You moved the wafers on a pair of tweezers, you spun the photoresist on, and you put them in an oven to dry them off. One day, during this process, the oven, for what it was worth, one of the engineers looked in to see how it was going and discovered this. Now, for those of you who don't know what it is, it's a meat pie. One of the technicians thought it was a good idea, it was a nice warm oven, to be able to warm up his lunch. And it's not his meat pie, by the way, this is a later meat pie. But that was the state we were in technologically at the time. Having already worked with all these things before, what became clear is that the way of doing this was to regard the diode as a capacitance or a capacitor in parallel with a current generator. You're all possibly familiar with that. And if you charge it up, shine light on it, it discharged. nothing particularly clever about that, but how do you extract the signal? And the obvious way is to put the charge back in and measure it. So that was one way we looked at, and this was a thing that was published a couple of years after we drew this out. So you had a line switch and basically a vertical and a horizontal line switch to select a pixel, and you measured the charge. Simple. The problem with that is that the charge is not only dependent on the light level, but also the area of the sensor and so on. It introduces a lot of noise, and a small detail, a charge amplifier at that scale didn't really exist at the time in a way that we could use. So then, and by the way, the drawings I'm going to show you are the original drawings. I haven't sketched them up. My writing has got considerably worse since I did this, trust me. So we went to a basic elemental pixel to charge the diode up, and then simply watch the voltage decay, which it would do with time. And the decay rate, obviously, proportional to the light. It was as simple as that, and that was the first drawing we did in something like May, it might have been June '66. We then moved on, or at least I moved on, and thought, well, why don't we put some switches in so we can select them? And this essentially is the line scan version. So you sample the voltage, and the following time when you sample the next one, you charge the previous one. Hence, line scan, and along the edge of the chip, all you need to do is put a shift register, says he glibly. So that's the simple way of generating a line scan system and a pixel. And you go to 2 dimensions, and make a 2-dimensional array, and that's the original drawing, which even I didn't understand when I found it recently. Basically, it's very simple. You just have 2 switches, and you just switch the output out. So that was the basic system we did. If we move on to the next phase, we were looking at all sorts of ways and all sorts of things we could do. This device we had to make. Nobody really made anything like this before, which was a bit of an issue. For example, let's take the 5K, the 5 meg scan rate. At the time, MOS couldn't do this. So I cheated, and I decided that instead of an MOS resistor, effectively, for the resistor of the scanning, I decided to use a diffused resistor. And obviously that's going to consume a lot of power. So we ended up creating a chip which generated 4 watts of power to achieve this goal. But we did get the scan speed there. It did crank up to that. We also decided to look at how low a light level we could get. And I spent somebody went pit. I spent a happy hour or 2 at night out in the moonlight, seeing if we could see things in the dark, as it were. And to some extent, we could, but then it just followed normal theory. We also tried all sorts of things. The first thing we made was a 7x1 array. We thought we'd be adventurous and make an array that was a linear array, just 7 pixels long. And it worked, much to the surprise of many people. Well, we obviously have other limits too. This is all optical. The whole thing was an optically based system. And remember, at this time, there weren't any computers and computer-guided systems or robots or nothing. It was all done by hand. So you generated the layers of masks effectively almost mechanically, and the step and repeat was done by basically one company, I think was based in Scotland, who produced the step and repeat mask. So there was an accuracy issue all over the place. And I thought it might be interesting to show you the design criteria. I'm not expecting to, I don't use slides in order to talk about the detail, but essentially, where you talk about pixels on a 1 micron pitch, I talk about nothing on 1 micron. There wasn't anything there. A contact pad size was 100 micron square, into which you could put 10,000 pixels today. That's the scale that we were working to. And you couldn't tighten up on this because it was all optics, and most people know what the wavelength of light is and how it works. So that was the sort of limiting structure we worked with. It also meant that if we were going to make any size array for true vision, it was going to be the size of an A4 sheet. The slices at the time of silicon were something like 1 inch diameter, 2.5 centimeters. When I started my own company 3 or 4 years later, they had rocketed up to 50 millimeters diameter. But that was what we worked with. We then looked at various ways of doing things. We looked at the, if you look at that, you're going to end up with the idea that a linear scan device, the closest you could get the pixels together would be something like 25 micron. And that was your ultimate limit. And to do that, you had to put the scanning on both sides of the array as well, because you couldn't get a shift resistor element, if that's the right word, into that length. If you're going to a two-dimensional array, because of the switch gear and the active pixel and whatever, and the scanning around the edge, 75, 80 microns is about, or was about, the limit. And that is the sort of sketch. We looked at making a 10 by 10 to see how it would work. And this was the original sketch, which I found somewhere in my papers. Again, pointing out that everything we did was manual, including all the papers written and everything else, which caused some excitement in the typing pool when you did put out a lot of theoretical physics. Then we thought, well, let's make one. And that was the first one. That was, whatever it was, 66, 67 probably. That's a two-dimensional array, 10 by 10, which worked. I discovered when I went back over this that we'd actually made 2 different sorts. And to this day, I don't know why, but we did. And I presented this as a paper in Eastbourne, I think, somewhere. The first time I talked about it in public, and threw that up on the screen. There it was. However, what I didn't know, that in the audience, if I can regard you as an audience, the audience I had, I thought were scientists, but there was a guy there from a national newspaper, and he published it nationally across the UK a couple of days later. That was the article, which I don't, that is the original, the black bits around the edge are what happens to sellotape or sticky tape after sort of 45, 50 years. And the coin they used as an example of how big it was went out of circulation in 1970, I think, 71. So that was published. Now, the reason I tell you this, and it was also published in the Today newspaper as well at the time, and maybe others, I don't know. We didn't have a clipping service to find out what was done. But as a result of this, I got, at least the company got calls from television companies, would I go on television and talk about it? Now, in those days, control in companies was so hierarchical that if the word television appeared, they had somebody up the hierarchy who said, I will go on television because I'm important. You knew nothing, but he was important. So I hope I've not insulted anybody here today, by the way. But the whole point is, there was an internal argument that went on because I had to get permission. That's the way it worked. Eventually, they caved in and said, yes, I can go on television. And I no doubt they were scared witless as to what I would say, because clearly I had no experience of being on television. I was just a youngster in the lab. And as you can tell, I have no ability to talk to people. So I went on TV. The result of that was quite interesting because in those days they planned the interview. They asked me questions, I answered them, went through it a couple of times, fine. Good, all done. It went out live, and I sat there, and I admit, terrified, because there were people watching the other side of that lens, like we have today. And I sat there and went through the questions. I thought, oh, it's all right. And the last question, and have you invented the James Bond spy camera? Which came at me from left field, for those who play that strange game. And I said, I tend to think fairly quickly, even at my age. I said, you've been watching too many films. And left it at that. But it was a bit prophetic, if you think about it. We carried on work on the 72 by 5. The 72 by 5 was really a difficult one to make because of the scale, the speed, everything else. Because it was going to be a chip a centimetre long by whatever wide. We tried lots of experiments. And we never got, with a slice like that, there were only about 10 chips a slice. And we never actually got anywhere. We'd get bits of them working, but not the whole thing. So I resolved that we'd go in on the weekend, the whole team, and we'd work through the weekend when there was no interference, no lunch to cook, meat pies to warm up or whatever. And we went through the weekend. We processed 80 slices. And we had 3 slices with chips that worked on at the end of that, fully worked. And of those, one on one chip, a slice, one on another slice, and some on another slice. Now we come to the tricky bit. It had to be cut out. In those days, you cut out the chip by scribing it, as you do glass, and breaking it. I will carry on because I think you're working out where we're going with this. We ended up with, I think it was just 2 chips in the end because the key slice broke. The technician, a guy called John Hind, I remember him very well, he came to work for 3 days after that and sat at his desk and went home again. He couldn't move. He knew the importance of the work and we just let him sit at his desk because no idea what he was doing or thinking about, but he took it very hard, I'm afraid. In these days you'd have counselling, wouldn't you? So we ended up, and we made one, and this is the chip. 72 by 5 array was for optical character recognition applications. It worked, 5 megs. Now, that meant, at that point, we ended up with achieving the goal. And the company could then use these in the OCR machines they were making at another site. And suddenly, the company decided that the work I was doing was, whilst fascinating, they decided to roll back on it and do less. And they did, you know, we'd achieved the goal. There was obviously nowhere else to go, so there's no point doing any more work, was the attitude. So, you'll have gathered by now from other things I said, I don't do slowing down, still don't do slowing down. So I decided to set up my own company. And at the end of August '68, set about doing this. Now, 2 things happened. One of them was that they knew I was setting up and leaving, and taking 6 of my people with me, not all from the same lab, but from other places. And the company wasn't impressed with this, apparently. So they tried 2 things. First of all, they took me out to a magnificent dinner with the research director. And I said, I'm going, that's it. Give me all the dinners you like, I'm out of here. That's not what I said, but you know, I've learnt that phrase from Americans since. If you then take the other view, the following day, I was called into the office and threatened with legal action if I did it, which was just as impressive as the dinner. So we decided that we were going to go. And I'd already put a paper in for publication at a conference based on recharging the diode from the surface without having another device. It's a recharge from inversion layer system that I use later in my company. And the company said I couldn't present it, but it had been published, but I couldn't present it at the conference. And I went to the conference, and I sat thinking, okay, so what are they going to do? An hour before the presentation, obviously there was stuff going on behind the scenes. They came to me and said, well, okay, yes, you can present it. And I was totally unprepared. I guess that was deliberate and typical of the advanced management techniques in those days. Yeah, if I'm cynical, trust me. So I set up my own company, we set off, and we left, and we had to get all the equipment, get ourselves a place to put all the equipment, plant or factory. We had to get some money. That seemed like a good scheme. So we set about doing it, and in February of the following year, 69, I think it was, we had the place starting to build up, and in May of that year we started making our first integrated circuits. The game had changed for me because at that point we either had to make money or fail. There isn't any in between in this when you get there. So we made a lot of single detectors, individual devices, and so on. I don't know where I am on slides now. Somebody will tell me. We made a linear array, which that was 1,024 pixels long, which actually is an inch long as a chip, which isn't bad on a 2-inch slice. And they worked. We made a whole range of these things, and they were used for inspection, character recognition. We sent some into space deliberately. That's part of a space project, different encapsulation. And they were used for detecting thickness of things, width of things, cleanliness of bottles, all sorts of stuff. And it went very well. And we made money, much to the astonishment of other people. Around this time also, I went to what was called the National Research Development Corporation, a government body that put money into research. And I decided that the best thing to do was to get some money, put it into, and make a 64 by 64 array. You won't have heard this before, but a 4K array, as opposed to 4 meg. So we did, and that was the first 64 by 64 array. That one still exists. It's the only chip left in the world that I know of that exists. It's at home, carefully protected by my wife. I was going to bring it with me, but I've got 2 with me built into my cufflinks. They don't work, so don't worry. So if you want to see the chip, I'm wearing it. And this was it, working as a TV, basically as a TV camera. If anybody asks me who the lady is, I have no idea. She was one of our operatives that would assemble chips. She was the best looking operative. I think that's how she was chosen. But this worked basically as a TV camera. And as you can see, the image is actually, looks like an image of somebody. We were given an award for this. And it was the Queen's Award for Industry. And the person on the left is me receiving the award. You will notice differences. Believe it or not, that is not a wig. And on the right is the Lord Lieutenant who represented the Queen. The Queen was busy that day, otherwise she'd have come down to present it. Because it was the Queen's Award, after all. Before moving on, because I then put up an idea to the company chairman and to the government and everybody else who'd listened for a multi-chip sensor with an optical system to create a colour TV camera. And it would have meant bigger slices, different processing, a lot of investment over a period of time, and being the British, whose vision lasts about 18 months, after which they lose interest, I got nowhere with it. So I decided, in fact I was headhunted out to run another company at that point. But before I go out of my company into somewhere else, I thought, oh, there's the actual award. It's about 2 kilograms of plastic. I was going to bring it with me, but I suspect the security system might have wondered about it. We made line scan cameras. I wrote a book on the subject, flying backwards and forwards to the UK, to the USA when I was travelling. Light sense. I remember Mike Thompson's presentation where he used a similar phrase, which you read it as either sense light or light sense, and he used something that read both ways as well. And that was sheer coincidence. Maybe our minds run along the same way. I don't know. But basically, I decided that I was going to move on. But I think it's worth stating that in 1969 I was in America, and I visited Hewlett-Packard, Fairchild, and a few others. Still not sure why, but I did. And I was offered jobs. I was offered positions and jobs and money, which was out of this world compared to what I was doing. I mean, serious money in those days. And I turned it down because my wife, and we had a small baby who is now 47, and also had my company. And I wasn't going to ditch the company, and I didn't want to put any stress on the system. Had they asked me a year earlier, when we didn't have a baby and a company, it might have been different. But I have no regrets at all. There's more important things than money. I kept this. You can't read it probably from where you are. And it's probably, I don't know if it's in the book or not, I can't remember. But these were my expenses from a visit in December 1974. Dinner for 5 in America, $36.60. That's an interesting comparison, I think. I don't know whether you're able to do that today, Eric, are you? I went on to do consultancy. We did a lot of consulting. We did some work for people I worked on with Frost & Sullivan on forecasting and so on. I was also dragged into a group of ex-Plessey guys who wanted to develop a machine. They didn't know what. And I said, well, why not make a robotic machine for assembling printed circuit boards? And I looked after they all agreed, and I looked after the conceptual creation of the machine. And we had a software guy who had his own company, we had mechanical engineers, electronics engineers, and so on. And we cracked on, and we ended up with a machine which worked on time in 1985. So that's a lot of what I did during that time, a lot of consultancy work, telling companies what they probably didn't want to hear. If you go in as a consultant, particularly with my approach to life, I tell it as it is. I don't get involved in the internal politics of companies, and if they don't like it, well, that's just tough, actually. But because of my background in so many different spheres, and also different countries, you can actually analyse what a company, the best approach is. And I was going to tell a story about different countries, but there are too many different countries here who might be annoyed. But even though Eric did promise me there were no ripe tomatoes out the back, which I feared at one point. But if we use the lessons of history as a guide to the future and the work I did 50 years ago, if I project 50 years into the future and look back to now, what we're doing now is primitive. I'll leave you with that thought, because I can look back 50 years, truly, and see what was primitive then. I'm not suggesting you'll look back in 50 years and see that there were meat pies in your ovens. That's not going to happen. But you will see things that change. Convergent technology is something that has always interested me. the convergence of machinery. Why we had, at one time, about 80s I suppose, we had photocopiers, facsimile machines, printers, a whole range of, it's all in one machine. And I said to people, why don't you make one machine? And of course, anybody who did that would lose business, because they'd probably find that that wouldn't work. So what happened? It happened, and on my desk in my office is $160 worth of does everything. That's simple convergent technology, and that's the way a lot of things will go and are going. And by convergent technology, I'm more looking at a more fundamental situation. Electronics won't necessarily last forever or do everything. You need to bear in mind not just electronics, but mechanics, bioscience, material science, and these things will generate new concepts in the way the world moves. The trouble is, history has also shown that our inventions, creations, such as nuclear energy, is fine. The other side of it is hugely destructive. The internet, terrific for finding out what goes on, and at least for me, finding out what you guys are up to all the time as well, and reading papers that I wouldn't otherwise be able to see, and destructive because of cyber attacks. Everything we do has two sides. There's nothing you or I can do about it. It's down to politicians, which means there's nothing anybody can do about it. We know from recent presentations of the last 4 or 5 years that you can store a lot of data in different ways. You can use DNA, you can make DNA, and you can read DNA. So you can use DNA to store data. In simple terms, what we all use are ones and noughts. DNA uses the 4 basic building blocks, except that it lasts for a very long time, and you can get the entire storage of everything everybody has ever put on a computer, including all your computers and everybody else's, a whole lot into a small truck, which is a frightening thought. How the hell you read it is another matter. But maybe that's a way forward for storage. 2 things about the future I wanted to just touch on before I throw myself out this door, which I believe opens. One of them is, I looked at robots and robotics. Now, people talk about artificial intelligence. The reason they use the word artificial is because it has been created by man, not any other way. It's still intelligence. So intelligence is intelligence, whether it's a robotic system or you and I. The problem I see is people make robots. There was the Japanese Prime Minister was on TV this morning, as it happens, talking about an exoskeleton for helping people to walk, using the output from the neurological system to drive the legs, so that people could relearn to walk using that technique. We've all seen robots that can walk and fall over and get up. But they're programmed to react to that. They haven't learned to react to it. If you take a human baby, without the noise and the other effects, it is useless. I don't mean that rudely. In fact, it can't do anything. If we didn't look after it, it would never become an adult human. It learns of its own volition. It is learning how to live and how to react to the world through vision, hearing, gravity, and everything else. So, I pose the question, how about, instead of BIOS in a computer, you have a similar system at the centre part of a robotic device, which can learn of its own free will. You don't teach it, it learns, and if it falls over, it hurts, it gets up. It learns to recognise things, and it learns of its own volition. And I pose the question, somebody might be doing this for all I know, but I pose the question because where does that lead us? It leads us to a lot of robotic devices that can move, walk about, do things, and at the same time communicate, and they're strong. Maybe they'll get to the stage where they wonder why they have to put up with humans. think about it. My other ambition, personal ambition, is to make an eye that you could plug into a human being so they can see and read. We can use the neurological signals to drive prosthetic arms and legs, I just said, but also, can we feed into the brain a signal from a neurological device? Incidentally, this is a robot. I thought you'd like to see a robot. This is Titan. It's quite harmless. There's a chap inside walking about, but gives you an idea. What I'd like to do is create one of those that you can plug in. All of you can make the eye. What you can't do is plug it into the brain. And that's an ambition I have, and I don't know how to do it. I don't know whether anybody knows how to do it, but that is something that would be a huge advance. There are millions of blind people. I'm not talking about the money, I'm talking about helping people and human beings. There's a lot more we can do, a lot more I could talk about, distributed energy generation, all sorts of stuff, but I won't. I'd like to pay enormous tribute to the people, I'm going to read this because I'll forget, to the people who worked at the same time, most of whom I've met at the time, and one or two since. People like Paul Weimer, who was a gentle man. I knew him reasonably well. I met him at Princeton back in whatever it was. And Gene Weckler, Rudy Dyke, Schuster, Taller, Rogler, Horton, Sangster, Mike Tomsit, who flew over to England to talk to me last year sometime, and rather amazed my wife and the waitress, because the waitress came up, and it was an expensive place near me. I can't afford to go there, but these obviously can. As an ex-Englishman, now an American, I guess. He said, for the waitress, he said, "Do you realise you've got somebody famous here?" That's what he said. I thought, what an odd thing to say. The sad thing is that, of course, she knew me anyway, but not as famous, if you see what I mean. There's everybody where I live. People like Ed Snow, John Rado, and so on. I'd also like to acknowledge the people who worked around me. People like Peter Fry, Peter Hughes, Peter Bartlam. Not everybody was Peter, but there were four of them. In one of my research labs, the boss was a Peter, I was a Peter, my psychic was a Peter, and we had a technical assistant called Rita. Going on, apart from the Peters, Jerry Parsons, Thomas Chamberlain, who somebody mentioned to me this morning, and you tried to Brian Kroll and more engineers and so on. Before I finally finish, I'd like to thank Mike Tomsit for coming and meeting with me last year, to Johannes and Pierre and Albert for their work in everything they do for me and everybody else. And it was nice to meet Johannes on Skype. He looks just like that on Skype. So, no idea how that worked. And finally, for Eric Fossum, for rediscovering me, an overnight brief glimpse of fame. Thank you all.
One or two questions or comments? Questions or comments?
I'm very thick-skinned, you can say what you like.
Okay, good. Okay, over here.
Jeff Rayner from SC Microelectronics. So what was the very first digital camera, not your own design, that you bought, and what did you think of it? Did you characterise it?
I expect an easy question. Do you know, I think it must have been a VHS-based video recorder camera. I can't think of anything else. And I didn't think of it. I don't think of things. I just use them. If they don't work, I get grumpy. So, sorry, that's not a good answer. But my sons are both photographers, and it took them a long time to go away from film, incidentally. To go away from film and use these newfangled things. My son in America asked me to ask you questions about how you're going to improve things, but I thought I'd better not.
Well, yeah, with the
Thanks, Peter. That was fantastic. You know, I'm kind of curious. I don't want to bring up a sore topic at all, but so here you're working on arrays of massive pixel and active pixel sensors. You've got cameras working, and then along comes CCD.
What's that?
Yeah.
Can I stop you there for one moment? Just stay there, don't run away. Sorry, one thing I didn't say, but it's written here for me. I've largely ignored my notes because I lose track. But essentially, at one point I had this weird idea that if you put some metallization side by side in two layers with slight overlap, could you shift charge along? So we made it. Nobody knew why I made it, but I made it. I had it made. And you could shift charge along. But then I thought that's not going to be anything useful at all, so I gave it up.
So anyway, I'm just curious from a business point of view, business owner point of view, how did you kind of see the emergence of the CCD and kind of, what was going through your head at that time?
Well, I knew it was there, as it were, and it was carrying on, they're making larger and larger ones, but my focus had shifted when I set up my own company to making devices that you could sell to make money, because that was the focus. And if on the side I could get research money to develop things, I would. But I never considered using CCD because I guess looking at the structure and the physics and the way it worked, I considered that MOS was the best way to go. It's as simple as that. I may have missed something, but it's as simple as that.
Did you have any trouble with MOS stability issues in operating your circuits?
Probably. Eric, it's a long time ago.
My circuits are also failing, but I'm just curious.
Yeah, you did get failures, in the field failures, but you had the bathtub effect essentially, which we started to put things through some extra tests. But they were flown in space to stabilize satellites at one time, so they worked reasonably well and lasted reasonably well.
Thank you very much. Thank you.